what we're going to do is we're going to have a look at the Young's Modulus required practical, and I will talk you through that as well. So we've got a copper wire. The copper wire is at least 2 meters long, and the reason why the original length needs to be 2 meters long is to reduce uncertainty. We have got a mass. So what happens is we add additional force. We use mass times gravity to figure out the force. And what that does is that produces an extension. So you've got that hanging sticker, which is a fiducial marker over the top of 2 set squares. The reason we need 2 set squares is to make sure that the wire is perpendicular. And what happens is we're directly above, you can see that the ruler is in line with the sticker. That fiducial marker will move to the left, and we'll be able to use that to tell us what the extension is. For this to be even better, the millimetre readings should be underneath the sticker. Problems with this, there are kinks in the wire. The wire should be taut. Okay, we would be able to use this, the micrometer, to calculate the average diameter and then calculate the area. So if I place that, and what we will do is we will start to look at the notes. Okay, oh, thank you. I could edit this out, but I think it's important so you can see the whole process. Right, okay folks, so what we've got is Young's modulus equals force times by length divided by area times by the change in length. So if you get a 6-mark question on this, what I would do is I'd write down that equation and I'd talk about the different factors for calculating the Young's modulus. So for the force, we're going to use slotted masses of known value. Force is equal to mass times by 9.81, which is the unit for gravity on Earth. And we'd use at least 6 different values. And the reason why is so we can get a graph and plot that with confidence. For the length, the wire needs to be at least 2 meters long, and that's to reduce the uncertainty. And we use a tape measure to record that length. The tape measure has a resolution of 1 millimeter or 0.001 meters, 3 decimal places. For the area is pi times by diameter squared divided by 4. And for the cross-sectional area, we'd take 3 readings of that diameter and calculate the mean. And we'd use a micrometer to do that, and that's 5 decimal places. And that's for measuring the diameter. For the change in length, we've got 2 set squares, and that's to ensure that the ruler, or if you decide to use a vernier scale, to make sure that's parallel to the wire. We're using a fiducial marker to aid with measuring the extension to make a comparison, and we keep our eye above the scale to reduce parallax error to make sure that we are in line. If we decided to measure the extension with a ruler, that's 3 dp. If we decided to use a vernier scale, that's 4 dp. You would not be able to use a micrometer for this. You would have to use a travelling microscope, and that has the same resolution as a micrometer, and that's with the crosshairs. And what happens is you move the crosshairs along and you compare how far it's moved, and that is 5 dp. So travelling microscope is the most precise instrument. So what we do, 6 different values of the force, 6 different values of the change in length. We'd plot that in a table, and then what we'd end up is a graph that would go through the origin. Okay, area, so we'd get our 3 areas based on the 3 diameters that we've used and take the mean diameter, and that would be our area value that we'd need later. A note, we're assuming that the area is a constant. Okay, if you're going to do this super accurately, you'd measure the area every time that you've added a new mass. The original length is measured using a tape measure. So Young's modulus is force times by length divided by area times by change in length. What we need to do is put that equal to y equals mx plus c to figure out how to use this gradient to calculate the Young's modulus. If you did stress versus strain as an additional column, then you'd be able to just calculate the gradient that way. If you haven't done that, then your gradient divided by the area divided by the length as a value would give you the answer for your Young's modulus. If you switch these the other way around, you'd have to re-manipulate that. And what you'd need to do is be able to put that into y equals mx plus c, and you'd be able to then prove that that is the case. Thank you very much.